Welcome to LIB Academy, and in this video we are going to look at one of the decay series that actinide series undergoes, and one of them is uranium decay series. And this series is a 4n plus 2 series, and at the end of this video we'll get to know how is it or why is it 4n plus 2 decay series. Uranium 238 is unstable or is radioactive, and because of that, at times, at a given point, uranium 238 is going um, to decay and give us thorium 234. And because thorium 234 is not also stable, then the decay process will continue like that up to a stable nuclide, up to a point where we are going to get a stable nuclide and the decay generally stops. So in this process, it involves the emission of alpha and beta particles. And this is a standard thing you should know. But before we continue, what exactly is decay series? That is what I explained earlier. Because we have a radioactive nuclide that is unstable, is going to decay to give us a daughter nuclide, and this daughter nuclide is unstable and is going to further decay and to give us up to a point where we are going to get a stable nuclide. And this involves the emission of alpha and beta particles. So let's see how it's done. Before we continue, let's look at the nature of alpha particles and beta particles. Alpha particle, usually represented by a symbol this, has a mass of 4 and a proton number of 2. So we can also represent alpha particle by helium nuclide. It is equivalent to helium nuclide. So one of these is okay for you to use and represent alpha particle. Let's also look at a beta particle. For a beta particle, it has a mass of 0, and beta particle is simple an electron, a subscript of -1. So because these decays are going to involve the emission of alpha and beta particles, we can then continue and see how it's done. So you can see that if a substance undergoes alpha decay, let's say if we have an element with a mass of 24 and then a proton number of 5, and it undergoes alpha decays. That means this element produce an alpha particle. We are going to get our alpha particle here, mass of alpha particle 4, and then proton number of alpha particle, which is 2, right? And then the principle is that the mass at the reactant site should be equal to the total mass at the reactant site should be equal to the total mass at the product site, and the same thing will happen to the proton number 2. So if we have an element with an atomic mass of 24 undergoing an alpha decay, then what are we going to get? We see we have a mass of 4 here. Like, what mass do we need to add to 4 to give us 24? You see, it's definitely going to be 20, right? And then for the proton number, this one has an atomic number of 5. So what mass do we need to add 2 to get 5, which is 3, right? So 3. After this, how are we going to know the elements? We just look at the atomic number, not the mass number. Looking at the atomic number, we compare to the periodic table. Comparing this to the periodic table, we will see that lithium has an atomic number of 3. So this is a lithium. This is just for illustration sake, right? So now we know that if a substance will undergo alpha decay, there's going to be effect on mass and proton, and same thing will happen to beta decay. So now let's proceed. Now we have uranium 238, sorry, and we have uranium 238 here, 234 here, indicating that there was a decrease in mass, right, by 4. And we could see that there was also a decrease in atomic number by 2. So this is an alpha decay. And this one too, we have 234, 234, and then so here we have proton number increasing. So since there is an effect in proton number, it's definitely going to be a beta decay. Why? Because originally we have beta to have a subscript of -1, and for this to be 90, exactly 90, this -1 is subtracting from this -1 is subtracting from 91. So for us to get 90, which means we will have 91, this particle plus a beta particle which is -1. So 90 plus -1 is going to give us 90. Like we said earlier, the sum of masses at the product side should be the same as the sum of masses at the reactant side. So let's continue. So this undergoes a beta decay, beta, and here 234, 234, and effect in proton only. So this is going to be beta, and here 234, 230, deduction of 4, we have alpha. Note effect comes in when we have a mass problem. So 230 to 226, this is alpha, and then 226 to 222, this is also alpha. So 222 to 218, this is also going to give us alpha. And then 218 to 214, this is also alpha. So 214 to 214, and effect in what? This should be 3. So 214, 214, effect in only proton numbers. So this is going to be beta. Now we have 214, 214, 83, 84, effect in proton number. So this is also going to give us beta. So 214, 210, this is alpha. 21, 210, 210, effect in what? Let's see that. Let's check that one again. This will be 3. So 210, 210, 82, 83. So this is also going to give us beta. And 210, 210, 8384, effect in proton number. So this is beta. And these two, we have 210, 206, the effect in mass. So this is alpha. So there's a need for us to write the overall reaction in the uranium decay series, and to also know the number of alpha involved and number of beta particles also involved, and also more importantly, the number of steps also involved in the net equation. Like I told you earlier, we're also looking at a trick to draw this. As far as you know, this one will undergo alpha decay, there will be a reduction in mass, and then effect also in proton number. So you look at that. To look for the element that you have to get is to look at the atomic number, not the mass number. So you look at the mass, the atomic number that you get, then you compare it to the periodic table, then you get to know what what element is that. So counting our alphas and betas, we have 1, 2, 3, 4, 5, 6, 7, 8 alphas, 8 alpha particles. Counting our betas to 1, 2, 3, 4, 5, 6. We also have 6 beta particles. How many steps are involved in this reaction? Well, we just determined this by counting the number of arrows involved in the reaction. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 14 arrows, 14 steps. 14 steps. Now that we know the total alpha particles involved and beta particles involved, let's write our overall reaction or our net reaction, starting from uranium 238. So we know uranium 238, the atomic number 92, will react to give us, will decay to give us a final product here, lead 206. Mind you, all these reactions will give us a stable lead, lead nuclide, which is very stable. So the actinized decays, the types of decays that the actinized series undergoes will generally give us a lead nuclide. So now that we know that this are uranium 238 decay to give us a final product of lead, how many alphas were involved and how many betas were involved? So we got to 8 alpha particles, right? So 8 alpha particles involved, and then plus 6 beta particles. So that's it. This is the overall reaction for uranium decay series from uranium 238. If we should check the total masses from the product side and the total masses at the reactant side, it will be the same. So here we have 8 by 4, 8 by 4, which will give us 32. 32 plus 206 is definitely going plus 206, and then plus 6 by 0, which is 0, is going to give us 238. And we have 238 here. That means the masses are balanced. And for the atomic numbers too, we have 82 plus 2 here, which is 84. And then we have 82 here. So this is 82. 82 plus 8 by 2, which is going to give us 16, plus 6 by minus 1, minus 6. And this is going to give us 92. So atomic number is also balanced. So why is the reaction 4n plus 2 reaction? Well, to determine that, just look at the overall reaction. You can take any of the masses, either lead or uranium, right? And divide by 4. So 238 divided by 4 divided by 4. Or you can decide to take 206 divided by 4. So if you are going to get a whole number, if we get a whole number, then it is a 4n series. But if you get point something, a decimal number which is point 0.5, then it's going to be 4n plus 2 series. And looking at 206, it's going to give us 206 divided by 4 is going to give us 51.5. So we have a point 0.5, and a point 0.5 means it's a 4n plus 2 series. And then a whole number, exactly whole number, means it is a 4n series. And a 0.25 is 4n plus 1 series. And 0.75 is going to be 4n plus 3 series. So something 0.75, something 0.75, and here something 0.25, right? You get a number here and 0.25 point, and if you get exactly a whole number, it's going to give us and therefore n series. So before we conclude, let me give you the trick to just keep in your head. If you are asked, any questions under uranium decay series, then you'll be good to go. Because we know what alpha and beta decay down to the nuclide giving, we just have to know the number of the alphas, the number of alpha and beta in decay, emitters in the series, like in a sequential order, so that we know that um, and so that with that we can predict, we can write a reaction without without necessarily memorizing everything. So let's go. So with this, we know that after we counted our alpha and beta, I've gotten it to be like this in order: alpha, beta, and then we have 5 alphas. So this is the trick. Just know for uranium decay series, this is what you just have to keep in your mind. This is alpha, beta, beta, 5 alphas, then beta, beta, alpha, beta, beta, alpha. So you can just say ab 5 alpha, bar, bar, and you should know that your bar is a double alpha, right? So after alpha, you should know that it will start from uranium 338. So keep uranium 238 in your head. It's 238, sorry. It will start from uranium 238, atomic number 92. So keep it in your head. So first of all, you write your uranium 238, then you bring your arrow, you write your alpha. Then when you write your alpha, you subtract the mass and subtract the number of protons. Then what do you get? You compare the atomic number of what you get to the periodic table and write the element. Then you start again by beta and start by again by beta. Continue how to, when you get this point, this means that you are going to do for alpha 5 times. So after you are done, you go for beta, beta, and then alpha, beta, beta, alpha again. So that's it. Thank you for watching, and don't forget to look out for the other decay series problems.